Okay, so here's our x of n given, and this first problem is going to be discussing the discrete signals and their transformations. So here we have an x of n, and the first part of the problem is going to be to just write it out in terms of a linear combination of shifted and scaled discrete delta impulses. So what I like to do is just start from left to right. So we know that if we're just uh, a regular delta impulse will look something like this, right? And this will look something like, if you have a graph, this will look something like this, right? This is 1, right? So just starting from left from right, we'll start
With
over
a
here.
quick point of clarification, it should be a lollipop, not an arrow. An arrow implies just continuous.
Oh yeah, good point.
Continuous impulse.
Yeah, should be something like this. Thanks for hopping in. And we're going to start from left to right here. So starting over here, use orange. So basically, I'll just put the amplitude at the beginning. So we'll scale it by a -3 because that's the amplitude of it. And then we'll write our function. And then we're going to shift it by however much it is from 0, right? So you have a right to be negative. So since it's 5x or n units to the left, we're just going to write n plus 5. So this term represents this lollipop right here. Okay, so just moving on, we can basically do a bunch of these for each single lollipop and add them all together to get our total x of n. So now we've done this first one, so we'll put a little check. And now let's move on to the next one. So we're going to say -10. I got -10 because that's the y, or the amplitude value. And then our delta function. And it's scaled 4 units to the left, so it's going to be n plus 4. Okay, so I'm going to do a quick pause. Actually, I'll just write, yeah, I'll do a quick pause. This one's going to be 0, so let's ignore this one. Can anyone help me do this lollipop right here? Anybody know what this lollipop will be? Feel free to unmute or type in the chat.
Would it be negative -4 times n plus 2?
Yeah, perfect. Delta n plus 2. Beautiful. Okay, sweet. So that one's done. Boom. And now we're going to just keep going from left to right, and you'll get in the flow pretty quick. So then we'll do plus. I'm just going to start to this next line down here. So plus 4 delta n plus 1. And guys, please feel free to hop in if you have any questions or anything. Okay. So now this one's done. This one's 0, so we're going to skip it, guys. Now onto this one. So it's going to be plus 1. You don't have to write the 1, but I'll just write it just so it's clear. Plus 1 delta and -1. Now we're doing -1 because we're towards the right, guys. So don't forget, you have a right to be negative. So a negative value on the inside is going to shift you to the right, positive value to the left. So then we'll have plus.
Would the next one be +7? Okay. So would it be +7 times n minus 2?
Yes, beautiful. Beautiful. Let's have 2 people do the next 2 as well. So now we've just done this one and this one. So what are these last 2 going to be, guys? Start with this one. What's the one at n equals 3 going to be? Anybody know? Plus 6 n minus 3. Yeah, beautiful. Oops. Yeah. And what about this last one, guys? We have one more term, this last lollipop down here. This one in pink. Anybody know? The amplitude is going to be at -3, right, guys? And the n is going to be at 4. So it's going to be -3 delta and -4. So that's our answer for part A. Everyone feel pretty good? Okay, feel free to hop in or interrupt if you have any questions. So we've just finished this, guys. So now we know part A, erase some of this. We're going to hop right into part B. So this is our x of n signal, and we want to do some transformations. I'm going to just quickly copy this, move it down here. So guys, we have 4 different types of transformations in this. We have an amplitude shift of 1/4. And this is a good way to approach the problem, guys. Don't even start doing any math. Just look at the problem for a few seconds, think about what you actually have to do, and then make a game plan, and then you can start solving the question. We have an amplitude shift. We have a time scale. Here we have time shift. And an amplitude shift, guys, or a DC offset. Okay, and it's really important in the order in which you do these things. This is not amplitude shift, it's amplitude scale. I think I said scale, but wrote shift. Is it scale? Is it shift? Okay, and the first thing we're going to do, guys, is we're going to just start one by one. So like I said, the order in which you do things is very important. So the first thing you do when you have all these transformations is you're going to start by just time shifting. We have this whole signal here, our x of n, and we're going to start by shifting it 2 units to the left. The reason I know it's 2 is because there's a +2 in here, and it's going to be to the left because it's a plus sign. So let's start just trucking away. We're basically going to copy this entire signal, but we're just going to shift everything 2 units to the left. So you can just start from the right or the left, whichever you prefer. So we have a lollipop at n equals 4, and its amplitude is -3. We're going to start here at 2, lollipop here. And then we have one up here at n equals, might actually be nice to write it like this, guys. So we can write n equals 4, n equals 3, n equals 2, n equals 1. That's 0. It's still important to shift it though, guys. N equals 0, -1, -2. Okay. Yeah, so now we can just kind of look at these numbers, and in our head, it's a little easier. So now we can shift this lollipop at n equals 3 to n equals 1. That's going to be at 6. And all of my y-axis needs to be fixed. So let's start here, 2, 4, 6, 8, all the way to 10. And once you do it the first time, guys, it's a little bit easier because you can just kind of copy paste. I'll show you what I mean in a second. All right, so let's just start from the top once more. It's good practice, guys. Watching me mess up in real time. N equals 4, we're going to move that 2 units to the left, and it's going to be at -3. It's going to be right here. Then we'll have n equals +3 up here, so that's going to be n equals 1 at 6. There we go. This n equals 2 is going to be 0. So we're going to move that over 2 units. Is at 7, something like this. So everyone feel pretty good so far? We're just going to keep moving everything 1 unit to the left. So this n equals 1 is going to be -1. Then 0. And then this -1 is going to be -3. That's at 4. And might also be nice to check them off, guys. This way you don't make any mistakes. So we just did n equals -4 here. We'll do it in pink. N equals 3, n equals 2, n equals 1, 0, and -1. So now we're on n equals -2. That's going to be -4. And it's at -4. So that's good. We'll do -3. So that's going to be at -5. It's going to be 0. And we'll check that off as well. And then at -10, amplitude for this one. So we just did this one. And then -5 becomes -7. And that's at -3. Everyone feeling pretty good so far, guys? Any questions? Okay, so the next step, guys, is going to be, we're going to time scale by 1/3. So does anybody know, is this going to be a time scale, a time stretch, or a time shrink? Wouldn't it be n minus 3? Or which one?
It will be a stretch.
It would be a stretchery. Perfect. I see a comment in the chat. Wouldn't it be n minus 3? Did I mess up somewhere, guys?
I like flipped the way I was looking at it. I got it. Thank you though.
Okay, sweet. Definitely let us know if you have any questions. Okay, perfect, guys. So it's a stretch. How do you know it's a stretch? What looking at this, how did you know it was a stretch? For those maybe who didn't get it right away. So we have a 1/3 here, and the reason they know it's a stretch is because it's less than 1. So when you have, for example, if you were to have 3n, that would be a time shrink, but because it's 1/3 n, 1/3 less than 1, yeah, exactly, Melanie. It's going to be a time stretch. So basically, a little trick you can do, which might be a little tricky on the test, just because you're not gonna have an iPad, but you can basically redraw the same axes. I'll move it down here just for clarity. You can basically redraw the same axes and then just change the x-axis, so numbers themselves. So I would highly recommend doing that on the test as well. It'll, you're gonna have to redraw the axes themselves, but you can basically just erase them and then just times them by 3. So here it's gonna be 18, right? I'll do it in red so it's a little easier. All right, so it'll be 12. This will be 6. And just for these ones, so it's a little bit cleaner, we'll erase them. But you guys get the point. So that way, it's a little bit easier in terms of you don't have to think about stretching out your axes and having these huge axes. You can just change the x-axis numbers themselves. So -6, -12, -18. Does that make sense to everybody, how I did that? That way you don't have to redraw the whole axes and make these huge axes. You can just copy the same exact graph, erase the numbers, and just times them by 3. Okay? So now we're on to step 3. And like I said, guys, do your best to try to, I'm not a big advocate for memorizing, but you might have to memorize the order in which you do these because the order is very important. You cannot do these in any order you wanted to. There's a certain order you have to go about them. So the next step, to recap, the first one we did was a time shift, then we time scaled, and now we move outside of the brackets, outside of the, inside of the X, we move outside of these brackets, and now we're on the outside of the brackets, so we're gonna deal with the amplitude now. So we're going to do an amplitude scale. And is this gonna be a stretch or a shrink, guys? It's a 1/4. So is this an amplitude stretch or a shrink? Perfect, Drew. How'd you know that? Because it was less than 1, right? So it's kind of flipped. When you're dealing inside the brackets, if it's less than 1, it's a stretch. But if it's outside the brackets, it's going to be a shrink. So it's going to be amplitude shrink. So it's kind of backwards, guys, don't forget. Because 1/4 less than 1. Let's go back up here. And we haven't, we haven't seen the test, guys, but these might be good, multiple choice conceptual questions to think about. So it's good to know these time shrink and just get some intuition about what you're doing. Okay, so another trick you can do, once again, is just copy paste this and then divide the y-axis by 4. So we can bring this down here. Erase this. Okay, any questions so far, guys? Everyone feeling pretty good? So now we're on to amplitude scaling. So what we're gonna do is just divide all these y-axes by 4. Okay, so this is going to be, actually, yeah, we'll just write it out in red so it's a little obvious. So now this is going to be 2/4, which is 0.5, right? This is going to be 1. I'm getting these numbers because I'm just dividing them by this 4 here, guys. So this is going to be 6/4, so 1.5. This is going to be 2. It's going to be 2.5. etc. Okay, and these will be the same. Just so it's a little less chaos. Okay. And once again, guys, feel free to interrupt if you have any questions. Okay, so we're on our last step, guys. So let's think about the actual problem itself. The actual problem was we had this x of n. We had to do these 4 transformations. We're starting step by step, doing one transformation, building on top of the other. And we're on the last transformation now. So now we're just going to amplitude shift by +1. Okay? So step 4 here. Step 4 is going to be the final answer. So now we're going to combine all of our steps. And this is going to be the step for this, the part for this step is going to be this +1. So now we're going to amplitude shift. Okay, so now all of our axes are nice. We know they're accurate. There's no negative, so there's no reversal in any direction. So we can just copy this and just add 1 to all the values, okay? So let's get rid of the chaos. And like I said, we're just going to add 1 to all the values. So here, it might be nice to actually write out the values just so there's no probability that you're messing anything up. This is minus 0.75. This is minus 2.5. Minus 1. I probably should have aligned it with the grids. That'd be nice. So it's very clear to you guys. Okay. So minus 1, this is 0, right? We still have to add 1 to these guys. These are 0. This is 1. 0.5. 1.75. 1.5. And the reason I'm writing it out, guys, is then we don't have to, continuously check. We know what the numbers are. It's like a table. We can just add them. It'll be easier that way. You'll see what I mean in a second. So now we can just maybe in a new color. Let's see. Lots of colors, guys. Let's erase these red ones. I was Bob Ross for Halloween, guys, so I have to use lots of colors. Okay, cool. So now so in orange, guys, is going to be from this step, and in red is going to be our new values. Okay. So this is going to be at 0.25. And if you're having doubts that it perfectly aligns on the test, you can just like write the number. I'm sure that'll be fine. So this is going to be minus 1.5 because we're just adding 1 to it. This is going to be at 1. And then we're going to have this at 0. This is at 2. This is going to be at 1. Does anybody know what this value would be? So for n equals minus 3, what's this value going to be, guys? So we're doing an amplitude shift of +1. Exactly. Yeah. So all we did for that was just 0.5 plus 1. Perfect. So 1.5. It's going to be 2.25 up here.
Wait, sorry, can you go up a little bit?
Yes.
I think it should be 1.25 for that one. Can you go up and check your work for that for n equals to 3, minus 3?
Yeah. N equals to minus 3.
So go up to step 2, please.
For here. Let me check the key real quick.
Step 2. Yeah, so 2.
Step 2, are you concerned about the y-axis or the x-axis? What do you think it should be for which point?
Wait, hold up. Did I do something wrong? We have 1. Okay, hold up. So x plus, you have 4, 1, yeah, it should be 1, not 2. There.
For which part are you looking at?
For step 2, where n equals
Hmm.
to -3. Can you go up to step 1 then?
Yes. This is exactly why you check your work, guys. You're getting in action.
Okay, you still have 2 there.
Yeah, so this should be
So then if you go
1,
to
right? Or no? Let me see.
yes, because if you look at the original graph, it's 1 and then shift it over 2.
Yeah,
Yeah,
exactly.
so that should
Okay.
be a 1.
You guys are all getting Fs because I was actually a test and none of you passed. No, I'm just joking. Okay, thanks for that. So this is exactly why you take your value. So maybe a good learning lesson is you should write the n value here, but also write the y value. So maybe I should have written something like n equals 4, and we could say y, or we could say x of n equals -3, guys. Whoops. And doing that for each point, and then you'll never make a mistake. So yeah, being a little bit more explicit here would be a good idea, guys. Okay, so let's go back quickly and fix this point. So we'll just have to change the amplitude. So this should be 1, guys. And this should also be down here. Okay, so in that case, this is 0.25, right? The old value. So then this becomes 1.25. Is that correct?
Yep, I think that's what I have in my solutions, yeah.
Okay, cool. Okay, guys. Thank you for your patience. We're showing you perfect examples of why you need to check your work, especially on the test. And then this is 0.25. Okay. Sweet. So any questions so far, guys? This is going to be your answer. This is your final answer. What's in red? So a little recap is we gave you an x of n discrete signal, and then we had you do 4 transformations to it. The order really matters. So the first step we did time shifting, then we time scale. Since it's less than 1, it's a time shrink. Then we amplitude scale, because it's less than 1, it's an amplitude shrink. They're flips for time and amplitude. And for step 4, we just did a +1 to all the values.
All right, can I check it really fast? So I have
Yeah.
0.25, -1.5, 1, 0, 2, 1, 1.25, 2.75, 2.5, 0.25, and 1. You're missing a 1 at the end, and it should be 2.75 for n equals to 0.
Yeah, so we didn't, I did not keep this 0 over here, guys. I put in 2 tests for you guys, and nobody caught the 2 tests. You guys are all failing. No, I'm just kidding. Okay, so let's add this as well. So we have 1 point over here. We still have to shift the zeros, guys. Okay, so then that's a 0. Well, 0 again. Okay, and then here that becomes a 1. Okay.
Right, so also everything after and before it, before that area should also be 1.
For which portion?
So the last one, the very last step. If you're going to keep drawing the rest of that graph, you also need to show at 12 it's 1, 15 is 1, 18 is 1.
Yeah, because it's like the DC shift, I guess, right?
Mm-hmm.
Okay. So you can just draw a dot, 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 guys.
And then also, I think at n equals to 0, I got 2.75.
Yeah, I just didn't add 1 properly. Okay. Thank you for checking my work.
Yeah, no, when I made these solutions, I used Python, so it's like it does all the math, all of tedious arithmetic for me.
Okay. Sweet. Any questions, guys? I think the key to this will be working through these problems yourselves. So definitely do your best to practice as much as possible. Practice makes permanent. And yeah, keep practicing and you guys will do great. Okay. So we have one more.
So another thing is what I would recommend for you guys is like try to do the problem without looking at the solutions for this exam review. And if you can get the right answer, then Yay. But yeah, I think it would be good practice for you guys to do it without looking at the solutions. Then you can check your answer with the solutions.
Okay. All right, so we have one more problem, guys. Let's power through this. So for this problem, it's going to be a little bit different. So here's this. Let's get a copy of this x of n. New copy, new problem. Okay, so once again, guys, let's just think about this conceptually before we hop into anything. So we have our x of n here, and we're multiplying it by two things. The first thing is this step function here, or two step functions. So two step functions being subtracted, and we'll draw them out later, but just for conceptual, basically we have a +2 here and a -2 here. So what this is saying is, we're basically really care about the region from -2 to +2, something in that region. And then we're saying we're going to multiply it by a cosine function that's dependent on the sample, on the n. So we're going to also multiply it by that, okay? So the first thing we're going to do is draw each of these separately because they're all being multiplied together. So let's draw each graph by themselves, and then we can multiply after that. So let's start off by just graphing u of n plus 2. It's really important that you start in the building blocks because then you're way less likely to make a mistake. So let's not do that in red. Oh my gosh, drawing a straight line is impossible, guys. Okay. Actually, nothing is impossible. There we go. So that's n plus 2. So if we were to just graph u of n, right, it would just be a step function. So you'd see something like this, right? These are polypops too, where everything after 0 is 1 and everything before is 0. So since we're going to do +2, we're going to shift it to the left by 2. So at n equals 2, or -2, right? Because it's +2. So you have a right to be positive. So because this is +2, we're going to be shifting it to the left. So at n equals -2 is when it's going to start being 1. Okay? It's going to be 1 forever. This will be 2. This is going to be 1 up there. And then everything before this, guys, is going to be 0. Okay? And inside this parentheses, we're subtracting this function by a u of n minus 2. So let's graph that too. Okay, so similarly, we shifted that to the left, and we're going to shift this one to the right because it's -2.
Do you have an iPad, or is that what you're using?
Yeah.
So Isabella is saying you can hold your pencil down for a couple of seconds after drawing a line and should automatically straighten it, which is a cool trick.
Isabella, you're a genius. Thank you so much. I will be taking advantage of that. Let's practice it, guys. Okay. Wow. That is incredible, guys. The era we live in. This is incredible. Okay. Thank you very much, Isabel. Yeah. Thank you very much. Okay. So now this is going to be the exact opposite, guys. So we're going to shift this to the right. So now it's only going to turn on to 1 after n equals 2. This is still 1. And it's going to be 0 at all points before this. Okay. So does everybody understand how I drew these so far? I'm going to assume that you do, but let's take a quick pause. Everybody understand me so far? So now we're basically going to subtract these two functions to create this inner parentheses. Okay. But once you start doing this more often, you start to just almost be able to do it in your head where you'll still have to think about like the boundary regions, but you'll get like a ballpark. Like, okay, we care about -2 to +2, but you still have to, do the math to make sure you're doing it right. But you'll see in a second here. So we're going to take this function minus this function. So u of n plus 2 minus u of n minus 2. So let's try to see at all times when these functions change. So basically, u of n plus 2 is going to be 1, after n equals -2. 0 before n equals -2. This is going to help you just kind of understand what's happening. So it really only changes at n equals -2. And the same can be said here for at n equals +2. So you have n plus 2. It's going to be 1 after n equals 2, and 0 before n equals 2. So what that means is we can kind of break these down into regions where it's going to change. So for before -2, we know they're both going to be 0. So we can graph that. It's going to be 1. Actually, what am I doing? I have to use Isabella's trick. Oh, wow, that's amazing. Okay. So before n equals -2, they're both 0. So this is also going to be 0 because we're subtracting them. So before n equals -2, they're both going to be 0. But then once we hit -2, this guy becomes 1. So if we want to break this up, at n equals -2, we're going to have this guy is going to be 1, right? So we're going to have 1 minus 0, right? Because this guy is still 0. So then this starts becoming 1. This is going to be 1. We can erase this just for our mental sanity. And nothing changes until n equals 2. Because at n equals 2, this guy jumps up to be 1. But this guy no longer changes anymore. They both only change at one time point. So we know this is going to keep being 1 until n equals 2. And once n equals 2 happens, we have to figure out what happens again. So this guy is still 1. So we're going to have 1 minus. And now this guy hops up to 1. It's going to be 1 minus 1. So now it's going to be 0 forever. Okay? Everybody understand me so far? This can be kind of confusing, but basically, if you have two functions like this, just start by graphing them and try to identify at time points in which they change. So this guy only changes once at n equals -2, and this guy changes at n equals 2. So you can evaluate your third function at those same time points whenever it changes. Does that make sense, guys? Any questions for how I got this? Okay, so
one thing to quickly note, notice that the subtraction does in the subtraction at n equals 2, the value is 0, not 1. And that's because you're subtracting, you're doing 1 minus 1. And so I would recommend to you guys to be really careful with that.
Yeah. Okay. Everyone following us? So now let's go back to our initial function. So we've successfully graphed this. So this has been graphed. So we can put a little check by it. And now we know that at any time points outside of these 4, no matter what, our function will be 0. So we can kind of already get a picture of like, okay, a lot of these are already going to become 0. But we still have one other term. We can't, get too ahead of ourselves. So we have one other term. Let's graph this guy. Cosine of n pi over 2. So let's graph this. And let's graph this in terms of it being multiplied to this function. So we're going to say cosine n pi over 2. And the reason I'm saying let's do it in terms of being multiplied to this is because there's no point of evaluating it after n equals 2 or before n equals -2 because we know it's already going to be 0. So it can save you some time on the test. You only have 4 time points that will not be 0. But let's evaluate this guy and see if that still holds true. Okay. So let's graph this. Okay. So now we're going to evaluate this guy at n equals -2, n equals -1, 0, and 1. So let's see, cosine of -2 times pi over 2. I got this -2 from this guy, right? So we're just plugging in n at the n values we care about, which is going to be the same as cosine minus pi. And then, just so you make sure you don't make any mistakes, guys, quick unit circle, 1, 0. Not really unit circle, but the boundaries, I mean, the axes. Okay, so at negative pi, it's going to be this guy. Cosine is going to be -1. Okay, let's do these other 4 values at the speed of light. Okay, cosine minus pi/2. It's going to be this guy. Okay, it's going to be 0 from this term here. And then let's do 0 times pi/2, which is going to be 0, which is going to be 1 from this term. And then cosine of 1 times pi/2 is going to give us cosine pi/2, which is going to give us 0. Okay, guys, so we have now evaluated our cosine function here at the 4 time points that exist in this function. Well, there's other ones that exist, but they're all going to be 0. So there's no point in evaluating it. Okay? Does anybody have any intuition for how these 4 points are going to turn out? Let's redraw this. So now we're multiplying it, guys. So what is the value going to be at n equals -2, guys? So we know that it's going to be this value times what? What's our new graph going to look like, guys? So we know that at n equals -2, this cosine function evaluates to -1. So it's going to be this value at -1. So let's draw that. So the orange, guys, is going to be the old values, and red's going to be the new. I'll erase them after so it's not too confusing. Okay, so here it's going to be -1. So how did I get that? We know that this function evaluated is 1 at n equals -2. And after multiplying it by the cosine and pi/2 of -1, we get that this is -1. Yep, exactly, Melanie. What do you guys think that it's going to be at n equals -1? Yeah, exactly. And what about at 0? So we got 1 for this. Exactly. You're rock star, Melanie. And then 0 again. So out of our initial x of n, we're only going to keep 2 values. So just as a recap, by subtracting these 2 unit step functions, we get that our entire x of n will be 0 except of these 4 values. And after going through one more step of multiplying it by cosine n pi/2, only 2 of those 4 values will not be 0. So we really only care about n equals -2 and n equals 0. Okay, so let's get that. Let's get our x of n. And we're basically going to make this 0 at every time point except those 2 time points at n equals -2 and n equals 0. So at 0, we're going to be multiplying our x of n by 1, right? Because this function is 1 at n equals 0. So now we're going to times this by x of n. Okay? So now this is going to be 0 because x of n is 0. So lots of zeros, guys. So this is 0 not because of what we're multiplying it by, but because actually the actual x of n is 0. Okay? And then let's do -2. -2 is going to be -1. So we're multiplying this -4 by -1. So that's going to be 4. And everything else is going to be 0, guys. So this is our new function, our answer. Any questions? I guarantee there's no stupid questions, guys. If I'm saying nonsense and you guys are confused, it's probably because of me and not you. So ask a question if you're confused. I guarantee somebody else has the same question. And you'll get the most out of this session by, asking questions when you're confused.
Wait, Phil, could you go up a little bit so I can see the other graph?
Yeah. This one?
Yes. Well, the graph is Yeah, it's that one. Okay, I understand how you got -2 for as 4, but what is 1, 0 for the final graph?
The final graph is 0 at n equals 0. Is that your question? It's because this guy is 0.
Oh, what's the final graph 0 at n equals 1?
At n equals 1.
But for 1,
it's because here. So when we evaluated, might be easier. So let me just start from the top and I'll do a quick review.
Oh, right. Okay,
Yeah.
right. That makes sense. Sorry, thank you.
Yeah. Okay.
Okay, thank you.
Yeah.
That makes sense. Sorry about that.
No, don't be sorry. Okay, so let's do a quick review, guys. So the initial
actually,
question.
Real quick on for n equals 2, how come that's 0?
For n equals 2, it's 0 because of this unit step function here. So basically, I'll do a super quick review and I'll mention that on the way down, Nick. How does that sound?
Good, yeah.
So we have this x of n function, guys. This is your question. You have an x of n function, and we're trying to answer the question, what is our new function, z of n, after we take this x of n and we multiply it by two things. The first thing we're going to multiply it by is this unit step function situation here. This in the parentheses. Okay, so we have two step functions in there, and we're subtracting them, and after we subtract them, we're multiplying this x of n by that. So this is our first guy we got to figure out. First guy to figure out. First guy. The second guy is this cosine of n pi over 2, which just oscillates as it's a cosine function. So some values will flip, some values will become 0, some values remain unchanged. So second guy. Okay. So we have two things we have to figure out. It's this unit step function situation and the cosine situation. So let's go back to the problem. So here's our x of n. And now, in order to figure out what this unit step function situation is, I just started by graphing the initial things first. So you want to start with the building block. Start with the simplest thing first. So start by graphing just this simple guy and this simple guy. And then it'll be easier to figure out their overall graph. So here, we started by just graphing u of n plus 2. So u of n looks like it's going to be 1 after 0. Starting at 0, it'll be 1 until infinity, and 0 at all points before that. Okay? So because this is u of n plus 2, we're shifting that whole guy to the left by 2 points. So it's going to start becoming 1 at n equals minus 2, which is why this starts up here. So we're shifting that whole guy to the left because it's a plus 2. And then we're going to do the opposite because that's in the problem. So u of n minus 2. So now we're going to graph that guy because we're going to subtract these two. So it'll make it easier to subtract them if we know what they look like. You're less likely to make a mistake. So now let's graph that. It's going to start becoming 1 at n equals plus 2 because you have a right to be negative. So a minus 2 is going to shift it to the right. Okay, so now we graphed both of these things separately. Now we have to subtract them to figure out, because they're in a parentheses, they're going to be multiplying our x of n. So we got to figure out what their overall function is after we subtract them. So we're going to subtract this guy. We're going to subtract this graph minus this graph, okay? So you can do that point by point, but a nice way to do it is just looking at points at which they change. So here we know that they're both 0 before n equals minus 2. So you already know that before minus 2, this is going to be 0. Let's highlight this too, so it's obvious. So we're plotting their subtraction, okay? And then once we get to minus 2, this guy comes up to be 1. So we're going to have 1 minus 0 at n equals minus 2. Okay, because this graph is 1 at n equals minus 2, and this graph is 0. So 1 minus 0 gives us this 1 here, guys. Okay, and then at all points in between, at all points in between from -2 to 1, this guy is still 1, but this guy is still 0. So this guy is going to be 1. Their subtraction will be 1. You have 1 minus 0, 1 minus 0, 1 minus 0, 1 minus 0. But then, once we hit to +2, this guy remains 1, so we're okay there. But now this guy changes. He becomes +1. So now we have 1 minus 1, which gives us 0. So basically, we started by graphing these two unit step functions separately, and we subtracted them. And the subtraction gives us that everything will be 0 in the function except these 4 points. And what that means overall is that when we multiply it to our x of n function, only 4 points at the maximum will be non-zero. Okay? But then we have one more term to worry about. So we only figured out the first guy. We have to figure out the second guy next, this guy. So then we can start graphing that. And I started by graphing its multiplication with the unit step function, because there's no point doing -5, -5, oh, whoops, jeez, -5, -4, right? There's no point if we know that's going to be 0 anyways because of this guy. So I only did cosine of n pi over 2 at these 4 timestamps, these 4 samples, because it's going to be 0 either way. So by doing that, we got these. So at n equals -2, it's going to be -1. N equals -1, it's going to be 0, 0 going to be 1, etc. So after we have these values and we multiply these values at these timestamps to this, we get this. So cosine n pi over 2 times these unit step functions subtracted. So we're multiplying the second guy by the first guy, and we get this. Okay. So what this means is now we only care about two timestamps, n equals -2 and n equals 0. And by care, I just mean those will be the non-zero ones, right? Everything else will be 0 no matter what. And so now we're ready. We have all this extra stuff that's being multiplied to our x of n. We have all the extra stuff figured out, and we have to just actually multiply it to the initial function to get a z of n. So this could be z of n. Might be good to label that. This is our answer. And so we know everything will be 0 except n equals -2 and n equals 0. So when we go here, everything's going to be 0 except these two timestamps. And then n of -2 just gets flipped. So here it's -4. And it becomes +4 here because it's times -1 from this graph. And then x of n at 0 is already 0. So 1 times 0 gives you this 0. Does that make sense? It wasn't really a quick review, but anybody else still confused? Does that help, Luke and Nicholas? Okay. Nick, are you okay? I'm gonna take that as it. You're okay. Any other questions, guys? Okay. If there's no other questions, I will pass it to the next person.
That would be me. Can I share screen, Paul?
Yeah.
Thank you. All right. Right here. Okay. So to the person who couldn't find the exam 3 review, it's under modules, and it's in the same like recitation section. It's in the same like recitation section with the recitation files. So yeah, click on exam 3 review. So I will be doing number 2, which is number 2, which is taking the same x of n as in the first problem and decomposing it into its even and odd components and also sketching them. And so for this question, I'll be using whiteboard. There's a chat. Oh yeah, reviews is that's where it is, review. All right, so I'm gonna start a whiteboard. Loading. All right. Can people see? I see. Okay, I see people's cursors. All right, let me go ahead and paste the question in. Zoom. Where? Zoom. There you are. Okay, so this is the question. All right. So as a quick review, if we have a signal here, which is x of n, the way we decompose it into its even and odds components is using these formula here. So what we do is we have x of n. We got to figure out what x of minus n is. We got to add the two signals together, and then take 1/2 of the amplitude. For odd, it's kind of similar. For x from the original signal, and then also take half the amplitude. Okay, so we have our x of n here, and what I'm going to do is to have people draw out x of minus n. So let me move that here to the right. All right, so can someone please help me draw x of minus n? Melanie, all right, I see your cursor, so you've been voluntold. Thank you, Melanie. Right, and so for anyone who's a little bit confused, x of minus n means that we flip the signal over the vertical axis, and so that's what Melanie is drawing here. All right, thanks, Melanie, and Alpha for helping label things. Ruhi, do you mind erasing that? Or actually, I can delete it. Ruhi, I'm gonna delete your delta function so people don't get confused, if that's okay. But thank you for contributing. All right, and let me go ahead and write in some of these values. So this is so this is -3. This is 6. This is the value of this is 7. Value of this is 1. Value of this is 4. Value of this is -4. This is -10. And this is -3. All right, great. So now we have x of minus n. And so I guess let's start with the even component. So in the even component, you would start by adding these two signals. So taking x of n and adding it to x of minus n for each n. And so Ruhi, do you want to try that since you seemed kind of eager to contribute in the last one? So in this graph down here at the bottom, can you just add x of n and it's x. There we go. X. Oh, I know why. Huh. Because I didn't make it wide enough. What? Yeah, so x of n plus x of minus n. All right, have at it, Ruby. Oh, I drew the little axis like below the. Do you want me to move it? Right here. Can you go to the left? There you go, right there.
Oh, okay. I am not good at like the graphs, so
Okay.
that's why I did not do a lot last time.
Okay, that's not a problem. So, what
I
would you
could-
prefer? Do you prefer a chart then, maybe, like in the form of a table? Does that work a little better
Well,
for you?
yes, but anything that works better for everyone. If most people want like a table or a
Well, how about
graph.
this? How about this? Let's do both. So, how about you do a table and someone else does a graph, and then we can see use your answers to check each other. How does that sound?
Okay,
Okay.
that's
So,
good.
Ruhi, do you want to do a table just somewhere on the side? And who wants to do the graph
Okay.
then? I'm gonna pick on Elizabeth because why did I say that? Isabella, because I saw her cursor. Isabella, you want to try doing the graph for x of n plus x of minus n?
Sure.
Okay, great. And then you and Ruhi can check y'all's answers with each other. And I have mine too, so. Doesn't look like anyone's drawing anything. Are you guys doing okay? Okay, I see a line from Isabella.
Sorry, I couldn't find my stylus. I had to just draw with my finger.
Okay, let me go ahead and delete my lines then. Here you go. Ruhi, how are you doing? Oh, I see her tiny
Doing
text
good.
over there. No, I see it now. Okay, so I will say we're running a little low on time. It's already been an hour and we're only on question 2. So let's only do the even component. We will provide you with the solutions for the review, and the odd component will be in the solution. So I highly recommend that you guys try the odd component at home and check your solutions against what it has there. But yeah, in this time we're only going to do the even. Isabella, you doing okay?
Yeah, sorry, I can't draw with my fingers. I switched to my iPad.
Okay, do you want me to just do it, or
Let me
if you're having issues with the interface?
Yeah, I can just redraw this.
Okay, I can, let me go ahead and do it. How does that sound? Looks like you're having trouble drawing things.
I think I can get it now.
Oh, wait, nope, sorry. You can, I mean, you can do the 1/2 if you want.
Sure.
Might be faster. But essentially, for everyone who's kind of watching, the process would be to take it point by point and add the points in each graph and then take half of the amplitude. So as an example, for n equals to -5, the value of x of n at n equals to -5 is -3. The value of x of minus n at -5 is 0. And so -3 plus 1.5. Uh, and so that's what you should get for that, for the even component for n equals to -5. Okay. Yeah, looks like you're doing good, Isabella. Let me take a look at how Ruki's doing. Although I will say Ruki's beating you, Isabella. I don't know if that matters to you or not.
It's fine.
Isabella, so I will say for n equals to -4, for n equals to -4, it's -10 plus 1, 2, 3, 4. -10 plus -3, so you get -13.
Divided by 2, isn't that?
Yeah, -13 divided by 2 is -6.5. So this should be,
Yeah.
yeah, -6.5.
Um,
Another thing you could do is just like not draw the y-axis like you have here.
yeah.
So what I do is just literally like not worry about scale and just write the amplitude straight on it.
Okay.
For me, it's just faster.
Yeah, it's probably faster.
Ruhi, you're doing well. You're almost done. Okay, it looks like you're also making a couple of arithmetic mistakes, Isabella. So for -3, it should be 3. For -2, it should be 1.5. Do you want me to take over? So for -3, it
yeah, I
should
see
be
that. I just wrote down. I'm just confusing myself with my scaling, so
yeah. Batul, sorry, what do you mean by that question? Can I please write down what I just said about adding the points? What did I say? You there, Batul? Hey. Well, feel free to type what it is you want to say. If you maybe don't want to talk, or if you just aren't at a convenient place to talk. All right, Ruhi, looks like you're done. Do you think you could evaluate those? So like, what would the actual numbers be?
Yes.
Great. So another thing I would recommend is putting parentheses around things. Oops. I can help you with that. I can take care of the parentheses, don't worry about it. Okay, looks like Batula's got it. But yeah, so I'm not entirely sure this is what you wanted, but essentially you would do it point by point. So for each individual n value, you would add the values for x of n and x of minus n, and then divide by 2. So if you take a look at Ruhi's work, that's basically what's going on here. And Isabella is over here on the left doing it in graph form. Ruhi, I'm gonna go ahead and start from the bottom, so it's a little faster. Uh-oh. Wait, did it disappear? Did I do something? Did I accidentally make your thing disappear?
I don't know.
Uh-oh. I'm so sorry.
No, it's okay. Don't worry about it.
You had all this hard work. Where did it go? It just
No,
disappeared.
it's okay. It's okay. Isabella's also doing a good job. So if anything, we can look at the graph first.
Well, I'm sorry about that. Something happened. Like all I did was, I don't know what happened. Okay. Well, I'm gonna go ahead and paste in our solutions. And Isabella, you think you're done? 1, 2, 3, 4, 5. Yeah, that looks. Would you say you're done, Isabella?
yeah. It's a little messy though, so sorry about that, y'all.
Not a problem. Okay, so I went ahead and pasted in. So this is the table that we have in our solutions. And the heck? Going on. Weird. Okay. So that's the table we have in our solutions, and this is the actual graph that I made using Python for the even component. So yeah, so -1.5, -6.5, 3, 1.5, 2.50, 2.5, 1.5, 3, and -6.5 and -1.5. Well, that's great. Okay, so it looks like you finally sorted out your scale list, Bella. All right, so it looks like we have the same answer. We'll go ahead and provide the solutions in a bit, and it will have the odd component. I would encourage you guys to do that at home without looking at the solutions, and then you can check. A quick thing is you guys can do a quick sanity check. So if you look at this graph, you can see that it is even, right? So if you flip it, if you reflect it, it's symmetric across the vertical axis. And so that's one way to check if you made a mistake somewhere, maybe. Because if it's not even, then maybe there's some arithmetic mistake. So, and same thing goes with the odd. So you can do a check to see if it's symmetric across the origin. Another quick check you can do is to see if the odd component and the even component, if you add them together, you should get the original signal, which is x of n. So that's a third sanity check that you guys can do if you have time on the test. But actually across the vertical or across the origin, that's definitely a super quick check. So, all right, so let's move on to the third question. I'm going to start a new page here. So at the bottom right, there's a little like 2 rectangles kind of ish with a 1. And I'm going to go ahead and add a page, and I'll be working on page 2. So if everyone can go to page 2, you can check to see if there's the 2 rectangles with the 2 at the bottom right. And let me know if you guys can't find it. So, all right, so the third one is going to be about discrete convolutions and finding what word am I looking for? The response to an LTI system. Okay, and so I pasted the problem here, and it gives you an h of n, and it gives you an x of n, and it asks you to find the y of n. So the basic steps are, well, first of all, I would graph h of n and x of n. I think personally that kind of helps you visualize things. And then the next step would be to express, okay, if it's not already, that step would be to express x as in the form of scaled and shifted deltas. It's already in that form, as you guys can see, so we can kind of skip that. And then the last step would be to replace the deltas with h's and evaluate the system response. Okay, so first of all, to graph h of n and x of n, let's see if we can do that really quick. So the process is pretty similar to what Will Knoll did in question 1. So to break it down into parts, let's first do a graph of u of n plus 2. And that's basically a u of n function, but shifted 2 units to the left, and he actually drew that already. And it looks a little something like this. All right, so guys, I am drawing with my mouse, and so these drawings are going to be incredibly horrible. I do apologize for that. But u of n minus 2 would look a little something like this. All right, and the next component of the graph is minus 2 times u of n. And so that is basically just a u of n function scaled with the amplitude scaled by -2. It should be close, I think. Close 26. All right, and that
we cannot find you.
Page 2.
Oh, cool. Thank you. Let's go to page 2, everyone.
Yeah, sorry about that. Page 2. So to go to page 2, you go to the bottom right where it has like 2 little rectangles, and it should say and you can click on that and go to page 2. All right, so -2 of u of n looks a little something like this. So it's essentially just a u of n function, but scaled, so that the amplitude is -2. So it looks a little something like that. All right, and the last one is u of n -2. So similar to the other one, it's the other problem. It is a step function, but shifted to the right by 2 units because of the whole right to be negative thing. So u of n is 2. So if I were to draw it out, it looks a little bit something like this. It's 2. All right, and so now we got to add all this up. So I think Will Knowles' strategy was pretty good in that you kind of just look at where the boundaries are. And so in this graph on the bottom, I'll be graphing h of n, which is the summation of these 3 graphs here at the top. And so that would look a little something like this. So it looks like we start at here. So there's definitely a lollipop at -2. And it looks like there would be a lollipop at -1 as well, because for these 2 graphs it's 0. Now here at n equals to 0, stuff starts to change. So you would, at n equals to 0, you would have 1 plus -2 plus 0, which would give you -1. And so at n equals to 0, you have a value of -1. And it would be the same for n equals to -1. Sorry, n equals to +1. It would have a value of -1. And now at 2, n equals to 2, that's when we need to start to take this third graph into account. And so the value of n at the value of h of n at n equals to 2 would be 1 -2 plus 1. So that would give you 0. And so h of n basically consists of 4 points where at -2 it's -1. Sorry, -2 and -1 it's has a value of 1, and at 0 and 1 it has a value of -1. Is everyone clear on this? Anyone have any questions for this, for how to draw h of n? Okay. All right. Well, I'm also gonna go ahead and draw x of n really quickly here on the side. So look to the left of the question, I guess. And so that should be, let's see how fast I can do this. All right, -3 is 1, and then it looks like it's 0 at -2. At -1, you get -1. At 0, you get 2. At 1, you get 1. And at 2, you get 0.5. So it looks a little something like this. So 0.5, 1, 2, -1. Okay, so now that we have our x of n and our h of n, now it's time to actually find the system response. So in the system response, we have to, the question is already expressed, x of n is already expressed in terms of deltas. So now to make y of n, we just replace all the deltas with h's. So we have h times n plus 3 minus h of n plus 1 plus 2h of n plus h of n minus 1 plus 0.5 h of n minus 2. And so this is our y function. Did I type that right? I think I typed that right. Yeah, that sounds about right. Okay, and so to find y of n, now then we have to kind of look at h of n and transform them according to these transformations. So in the interest of time, what I'm going to do is I'm going to be pasting a lot of graphs. Wait, nope. Okay. What I'm going to be doing is pasting a lot of some graphs into whiteboard and kind of explain how they were generated. And I would highly encourage you guys to kind of replicate the graphs at home. And so this is the graph for h of n plus 3. I'm basically just taking h of n, shifting it 3 units to the left, and that's what I get. Okay. For negative h of plus 1, h of n plus 1, I get this graph. And so to get this graph, I shift it over 1 unit to the left, and then flip the multiply the amplitude by -1. For 2h of n, I get where is it? Here we go. I get this for 2h of n, and for that, the next component is h of n minus 1, and I get something a little bit like this. So in this one, I just shift it over 1 unit to the right. And then the last component is right here, and it is 0.5 h of n minus 2. And so in here, I shift it 2 units to the right, and then multiply the what word am I looking for? Multiply the amplitude by 0.5. Okay, so that's each individual component of y of n, right? But to actually find y of n, you got to add all of these up. And so I'm going to paste the final plot here. Where is it?
Teresa, I had a question. Why did you start with the height at -2 again for 2h of n for
this one?
Yes.
Yeah, so this is just h of n, which we have right here, but it's scaled by 2, right? So instead of having
got it.
Yeah. All right. So I'm not going to bother doing the addition because it's kind of tedious, but if you add all these plots up, y of n over on the right is what we have. Some people like when they add these values up, some people like doing the graph. Ruhi, for example, likes doing a table. I personally prefer a table. But I would strongly suggest you guys kind of do whatever works for you. So yeah, I think that's it for me. Does anyone have any questions before we move on to number 4? We still have a lot to go and we have half an hour left. Okay, I'm gonna close this whiteboard. Actually, shoot, hold on. Amelia, if I have to save this as a PDF, how do I do
that? You can just leave it, it's fine. You can do it out of the meeting.
So if I close it, it should be.
Yeah, it will be saved. Yeah.
Okay, I'm gonna go ahead and do that. All right, and on to number 4.
All right, everyone. Uh, would you like me to go full question for number 4, and number 5? Because I know we have 3 questions on number 5, and we're kind of like short on time.
Sure.
Let's see. Let me share my screen. All right, can you see my screen, everyone? Can you hear me?
Yep, you're all good.
Cool. Thank you. Okay. So on number 4 here, let's do this question. So discrete time Fourier transform. We want to find x omega based on xn we have here. So we've already done similar question on recitation. So let's now try it again. Let's look at the table. The first step that you want to do when you see this type of problem is to look at the table. Can anyone give me suggestion of what property or pair should I use with this one?
One of the properties I would say it would be time shifting.
Time shifting. Actually, thank you for your answer. Actually, let's look at the pairs. I think the pairs will be more fit in this situation.
Yeah.
So we have n equal n plus 1, right? Times 0.25 to the power of n and un. So if we look at number 8 of the weighted exponential here, we're gonna have something like n plus 1 times a to the power of n and un, which is similar to what we want. I'm gonna snip this property. Take it with me here. Okay, so this is the pair. Sorry, I keep calling it property, but this is from the pair table. This is the thing we're gonna use. So, we want to find x omega and we x omega, but we were given xn, right? So x omega we would get that from applying discrete time Fourier transform to xn, which is signal in discrete time domain. And let's plug xn in here. So we got n plus 1 times 0.25 to the power of n times un. Okay, if we look at the property here, can anyone tell me what will be the value of a?
0.25.
Yes, 0.25. Thank you. So when I apply discrete time Fourier transform to this question, I'll just get this side, right? Apply dTFT and I'll get 1 over 1 minus 0.25, right? Times e to the power of negative j omega and square. And careful about the condition. Our a absolute value of a is between 1. So that means we're on the right track here, and that would be the answer for this question for problem 4. Now let's move on to problem 5. I'm gonna give example for 5A and 5B, and if you know the principle of 5A and 5B, you can do 5C easily. Okay, let's start with 5A. It would be a little bit trickier from this question, but okay, let's see. Anyone would like to try pointing to me what would be the relevant property or pairs I can use with this one? I give you a hint. Look at pair table, 6.2 table here. I get chat from somebody. Exponential. Yes, right, Bartul, thank you. It would be number 7, exponential. But, do you see something on exponential? It's just gonna be 1 over some terms, right? But what we have e to the power of something, right? Therefore, what we gonna do, we will break this term down into e to the power of negative 3j omega times 1 over 1 minus 0.4 e to the power of j omega, right? And from this is the multiplication in frequency domain. And if we look on table 6.1, multiplication of frequency domain, what happened in the time domain is that the two signals will be convolved together. And we gotta be careful about that. Okay, after we identify this, let's try to actually solve this problem. Okay, we want to find xn, which is signal in discrete time domain. Keep that in mind. And as I try to solve this x omega, which is e to the power of negative 3j omega 1 minus 0.4 e negative j omega, right? Which is the same as this term. Okay, so when I find my xn, I have to apply discrete time Fourier transform, but inverse. But now inverse. So, and I will plug x omega in of x omega. What I will get, I'll plug x omega that we just break down here in, and we will get e to the power of negative j 3j omega times this part. Okay. And because they're multiplying inside the bracket, what happened inside the bracket? They are in frequency domain, but when we break it down and when we change it to time domain, they will change from multiplication to convolution. So what I'll get is that This is what I get after I break down. Anyone have question on this part before I move on? Is it clear to you? Give me a thumbs up or say something. Okay, I assume everyone is cool with this. So let's move on. Let's see. We already identified this property here, which Bartu helped me is gonna be exponential. But we also have this part, right? Which will be, I'll give you a hint, is shifted impulse. A shifted impulse. And exponential. Therefore, can I move this, please? Okay. So if we look at first term, according to the first term with the shifted impulse pair, can anyone help me identify what my K will be? K here, what is it when I compare to e to the power of negative 3j omega? Three. Thank you, Melanie. It is gonna be 3. Therefore, we can easily do this first term now. What we get from the first term is delta function of n minus 3. And this is being convolved with this part. Can anyone tell me what A is? 0.4, thank you. So we will get 0.4 to the power of n times u n. And okay, other TA, please correct me if my information is not correct, but I think we can still where we have u of n convolved delta function that got time shifted by s unit, and then we'll get u n plus the time shifted. So we'll keep this in mind. And we can simplify our term further. Like, do you see something here? I have delta function. It got time shifted, and I have a unit function here. Therefore, my xn can still be simplified further as, let's look at this. un minus 3, right? And don't forget this term here. It's going to be 0.4 to the power of n. And that's
also going to be n minus 3 because the delta function is being, the delta function shifts the entire n, so 0.4 and then the u of n here. It shifts all functions, that's it.
Okay,
Yep.
it's everything. Thank you. So that's for question A. Now let's do question B. Why did we apply convolution for the inverse? I got. Oh, okay, Ruhi, I think you have question about what happened between these process, right? What happened during the process?
Yes.
It is because the two of this, they're in frequency domain, right?
Yes.
But multiplying each other. So if we
Okay.
look at table 6.1 for time convolution part, when we have the frequency domain that is multiplying each other, when we change them to time domain signal, the time signal will actually be convolving with each other.
Okay, thank you.
Okay, cool. And if you want to try question 5C later, you'll have to use this property too. I will give solution for that part as well. Okay, now let's try 5B. 5B. So have x omega equal e to the power of negative j omega square root of 2 with 2 minus e to the power of negative j omega square. Okay. Now let's look at the table that we have. Anyone would like to try and see what would be the pairs or properties that I should use to solve this question? I give you a hint, we should look at table 6.2. Okay, I think I can just help point to you here. Oh wait, I got some chat. Right, exponential. Oh wait, exponential, okay. Yeah, thank you, yes, it is the weight exponential. But do you see our term are not quite alike? The given pair, right? So we need to do some changing some transformation with our signal, so it would be able to work with this pair. Okay. And what I will do is, let's see, I will take out 2 from the bracket here, inside the bracket here. I'll take it outside. And we got to be careful because it being square. So the 2 that we take out from the bracket has to be squared as well. So let's try that, shall we? The top remain the same. Square root 2 is also the same. But now I take out 2 from the bracket and it has square. So it's going to be 2 squared times. So if I take 2 from here, what remains gonna be 1 minus 0.5 e to the power of negative j omega square. All right, everyone, please help me check if I make any mistake in this process. Okay, I'll continue. I'll separate these two from the term. So I'll have 1 over 2 over 5 over 2. A little bit confusing, but that's what we got. And this side, we'll have e to the power of negative j omega 1 over 1 minus 0.5 e to the power of negative j omega square. Okay. Now let's look back at the pair that we just identified. So we noticed that, okay, we got 0.5 here. Our A is likely going to be 0.5, right? But on the upper part here, we don't have 0.5. Where's my 0.5? I need that 0.5 to continue, right? So what I will do, I'll just multiply 0.5 on top and bottom. And let's simplify that further. We will get 1 over 0.5 is just going to be 2, right? So 2 over 2 over to the power of 5 over 2 times 0.5 e to the power of negative j omega over 1 minus 0.5 e to the power of negative j omega square. And now I can just apply the Fourier transform to this term easily. Okay. Before we continue, this is still x omega, but I want xn, which I can get from inverse discrete Fourier transform. Omega, what is it? Isn't it 1/2 to the power of 5 over 2? Here. Is 1 over 0.5, right? So that's equal to, so it should be 2 over 2 to the power of 5 over 2. Is that clear? Oh, okay, cool. Yeah. But thanks for catching that. I need someone to help me catch in case I made mistake. So that's a great start. Okay. That means we are doing inverse Fourier transform of this part 2 to the power of, okay, it's kind of complex here. So I'll simplify this further. And what I got from my simplification, I got to the power of negative 3 over 2, this part. After I simplify, I got this part. I just remain this and okay. This long chunk is gonna be the same. Oh. I just copy and paste them because I'm too lazy to write it out again. All right. Can anyone suggest me what I should proceed with this step? Should I have some choice for you. Should I use linearity or time convolution? This is the question. Can you explain where you got 2 to the power of negative 3 over 2? Okay, let's go. So, okay, I might be too quick on this, but we have 2, right? And 2 to the 5 over 2 is gonna be 2 to the power of negative 5 over 2. And our 2 is actually 2 to the power of 1, right? So this part is just equal to the power of 1 minus 5 over 2. So 2 to the power of 2 minus 5 over 2 is 2 to the power of negative 3 over 2. Okay, cool. Okay, let's move on. Okay, I give you answer here. So this part, we're not gonna use convolution with it because it's just a constant. Therefore, the property that we use here instead would be linearity because it's just a constant here. Therefore, what happened after I apply inverse Fourier transform to this? I'll just take 2 to the power of negative 3 over 2 outside. And I just apply inverse Fourier transform to, okay, this part. Copy and paste. Anyone would like to try giving me answer for this inverse Fourier transform? I'll give you a hint. Oh, did anyone want to say something? Okay, I'll just proceed on this because we are short on time. So the answer after we apply this inverse Fourier transform, we'll get n times 0.5 to the power of n times un. And that is our answer. Cool. And there's one more question on 5C. I didn't put it here, but you can try that if you like to see and taste yourself if you can do it. And that would be it for my part.
Okay. I'm going to try to go through, we have 2 more questions. I'm going to try to go through them as quickly and concisely as possible. Just because we are already at time. So if you have any questions, please jump in, but I'm going to try to move pretty quick here. So we're actually going to skip over question 6 and jump straight to question 7 for now. So we want to determine the minimum resolution for an analog to digital converter to handle an incoming signal ranging from -15 to 15 volts and have it be sensitive to at least 0.5 millivolts. Then we want to find the quantization of an error, the quantization error of an input signal of 1.5982 volts. So the first step with any of these kind of problems is we're going to go to this equation where we have delta is equal to R over 2n 2 to the power of n minus 1. this is going to be our signal resolution. This is our signal range. And then this N is what we are trying to solve for here, which is the bit resolution, or commonly just referred to as the resolution. So we want to solve for our N value. And how do we do that? So the first thing we need to determine is our sensitivity. So our sensitivity that we're shooting for is 0.5 millivolts. So our sensitivity is equal to 0.5 millivolts. Now, this means that our step size has to be smaller than 0.5 millivolts to be this sensitive. Because if our step size is bigger, we'll lose some data over 0.5 millivolts. So we can express that as delta has to be less than or equal to our sensitivity. Where this is, delta is our signal resolution or our step size. So now we can substitute in our equation for signal resolution. So we get R over 2 to the power of N minus 1 needs to be less than or equal to our sensitivity. So now we can plug in our values. So our R value, our signal is ranging from negative 15 to 15. So we're going to have 15 minus negative 15 volts divided by 2 to the power of N minus 1 needs to be less than or equal to our sensitivity, which is going to be 0.5 millivolts. So we can simplify this down to 30 volts over 2 to the power of N minus 1 is less than or equal to 0.5 millivolts. Now we can multiply our 2 to the power of N minus 1 over and divide by 0.5 millivolts. And that's going to give us 30 volts divided by 0.5 millivolts is less than or equal to 2 to the power of N minus 1. We can divide this out. And the easiest way to do this is to divide 30 by 0.5, which gives us 60, and then multiply that by 1,000 because the bottom is in millivolts. And that's going to give us 60,000 is less than or equal to 2 to the power of N minus 1. We're just going to add our N over. So we're going to get 60,000, or sorry, not our N, our 1. 60,001 is less than or equal to 2 to the power of N. And now we need to figure out what our N value is to make this equation true. So we're provided with a chart of 2 to the power of N's. And if we look at it, we see we need it to be greater than 60,000. And the first value greater than 60,000 is at 2 to the power of 16, which is going to be equal to 65,536. So 2 to the power of 16 is equal to 65,500 and what was it? 536, which is greater than our 60,001. Therefore, our N value is going to be 16. So that's the first part of the problem done. Does anybody have any questions there? And if anybody's typing in the chat, TAs, can you just let me know? Okay, I'm going to keep going. If you have any questions, feel free to shout them out or type them in the chat. So now the second part of this question is we want to find the quantization error of an input signal of 1.5982 volts. So the way we approach this is we need to figure out the difference between the analog input signal, which is given to us, and the quantized output signal, which we can calculate. So the first step of this is we need to take our bit value and we need to figure out what our actual step size is or our actual signal resolution when we use a value, a number of bits equal to 16. So the way we do that is we just go back to our equation. Delta is equal to R over 2 to the power of n minus 1, which is going to be equal to 30 volts over 2 to the power of 16 minus 1. And that's going to give us, let's see, .000458 volts. So each step is going to have a width of 0.458 millivolts. And that is our actual step size for our system.
Hi.
Yeah.
Hi. Excuse me. On the test, could we leave it as 30 volts divided by 65536 minus 1?
I think on the exam, you won't have such a large value, so I think you'll be able to solve it easier. I think if you do have such a large value, you might be able to. Your best bet would just to be approximate it to as close as you can and then run with that value and make sure it's clear that like this is an approximation and then use that value.
Okay.
Does that make sense? Okay.
Yes.
So then now we need to figure out how many steps does it take for us to get to our input value. And in this particular case, our signal range is from -15 to 15. And the easiest way to do this is to offset our system and our signal to be starting at 0. So the way we're going to do that is we're actually going to take our input signal of 1.5982 volts. And we're going to add 15 to it. And that's going to give us 16.5982 volts. And all that's doing is it's finding the difference from the floor of our range to the value. And we just do that by shifting it up to where our floor is at 0. Does that make sense?
Why did you add 15?
So because our system, we have it so that it's handling from -15 to 15 volts. And the easiest way to do the rest of this math is if you offset it to where your floor of your signal range is at 0. So we're basically shifting everything up by 15. So our signal range is from 0 to 30. And then our signal value that was 1.59 is now shifted to 16.59. Does that make sense?
Not really, but it's okay. You can keep going.
So no, I want to make sure you understand. So all we're really doing here is we're finding from the bottom of our floor to our value. So if the system was just from 0 to +15 volts, it would just be our input value, right? But because we have a floor of -15, we take that and add it to our value, and that gives us basically the total voltage between the floor of our system and our input. Did that clear it up?
So maybe you can draw kind of a diagram. So
yeah.
So like -15 at like the bottom, +15 at the top, and then 1.6, 1 point whatever is somewhere in the middle.
So this is our signal range, right? And let's say this is 0. And our input signal is somewhere around here at 1.59 82 volts. And we want to, in the next step, we're going to find the number of steps that it takes in our system to reach that value. So we want to find,
So
this is broken up.
Sorry,
Yeah.
so one more thing you can add to the diagram. So -15 would have a value of like 0, and 15 volts would have a value of like 6, would be like the 65,000 whatever level.
Oh, for the like number of steps.
Yeah.
Gotcha.
Does that help?
I can do that in a sec.
Yeah.
But so keep in mind, this whole thing is made up of a bunch of discrete steps, right? And we want to count the total number of steps between the bottom, which is our -15, and our input value. And the easiest way to do that is we add 15, and that shifts it so that it'll be like this. And now we can count the number of steps here more easily by simply dividing this value by our step size. Does that help clarify? Does that visualization help?
I don't know. I just like just keep going.
Okay.
It's fine.
So see if the next step makes it clear why we do that. So for our next step, we want to find the number of steps. And that's just going to be our input signal that we shifted divided by our step size, which we calculated up here. And that's going to give us 36,240.6 steps. And if we had done it with just our initial input signal value of 1.5982 divided by that value, we would have only gotten 3,490 roughly. Does that kind of, does that help you conceptualize why we shifted up?
I mean, not really, honestly, no, but it's okay.
Okay.
And we should do that for the add the 15 volts, or no matter what it is, for any question we have like this, right?
For if your floor is less than 0, you should add that value. So like if this was -5 to 5, we would add -5 or add 5 instead. Right.
Okay, so since it's -15 volts to 15 volts, it's
Yeah.
below 0. Okay, that makes sense. Thank you.
Okay.
Yeah, so I guess like if we were to take a look at that diagram, the distance between the like floor and the ceiling is 30 volts total. Going from -15 to +15. If you want to put it in terms of levels, it goes from level like 0 to level 65,000 whatever it is, 500 something. And so we're trying to convert between volts and levels, if that makes any sense. And so going from the bottom, this 1.5982 volts is 16.5982 volts from the floor. And we're trying to say, okay, in terms of levels, what's the conversion there from the floor? I don't know if expressing it that way makes it any clearer or no.
hopefully,
not.
if
Maybe
if you're
not.
still confused at the end, if you have the time to stick around, we can try to come back to it. But once we have our number of steps, we need to round this to our nearest step because we have to keep in mind that these are discrete steps. So that it has to be an integer. It can't be a decimal. So we're going to round this up to 36,241 steps. And that's the number of steps it takes to get to our input signal. So now we want to find the actual value at that number of steps because we rounded it. So the way we do that is by just multiplying by the step size once again. So we're going to multiply by our step size. And that is going to give us 16.5984 volts. And that's going to be the value at that point. So our 16.5982 value, this is our initial input. And then our 16.5984 value is our quantized output. And the way that we can solve for our quantization error is just by subtracting these. Then, sorry, I'm drawing a blank now. Teresa, do you take the absolute value?
Yes, you do.
Okay. And then you take the absolute value of it. So when we subtract these, we're going to get a difference of 0.0002 volts, which we can express as 0.2 millivolts. And that is going to be our quantization error. All right. Any questions on that? So we solved for our number of bits, and then we used that to solve for our quantization error.
Hi, I have a question.
Yeah.
Since we don't have a calculator, how much would you say we need to simplify? Like for 16.9592 divided by 7.000458, would that be acceptable to leave it at that?
So for that, a lot of the numbers would either be in. So for that, a lot of the numbers would either be in like powers of 2, or it would either be in powers of 2, or you could leave it as just like the expression. One of those two possibilities would be my guess.
Mm-hmm.
Okay, thank you.
Yep. Luke, I would recommend there's a question in recitation 9, and then there's also this question. And I would just recommend trying to do them on your own and compare to the answers provided. That would really be the best way of studying this. And then you can also go back through the notes and everything. But we do also have office hours as well. So if you study this and you're still confused, feel free to go to one of those to get clarification.
Yes, I think I'm gonna hop over to my office hours right around now.
Okay. Also for the tables on the exam, I'm not positive when they'll be given because I believe it's up to the professor to upload them. So unfortunately, I don't know that.
I'll write a reminder to him. A reminder
Okay.
email to him.
Thank you. So now we're going to jump back to question 6, and we're just going to do part A1 of this and part B. There is a second part to question A, but we're going to skip that, and I'll go ahead. You can try it, and I'll post the work for it. So we want to find the Fourier transform of x of t. So how are we going to approach this? The first step should always be, what do we have in our function x of t? In this case, both sections of the functions are just shifted delta functions. So we can go ahead and look at the table and see, okay, from the Fourier transform pairs, a delta function, Fourier transformed, is just equal to 1. So we know our expression is shifted delta functions. And we know if we have a signal that's just a delta function, our transform is just going to be equal to 1. Now we can go to the properties table and see when we time shift a time signal, it corresponds to a frequency shift in the frequency domain, which is the e to the minus j omega t naught times x of omega t. X of j omega. So we know if we have signal x of t minus t naught, we're going to get the transform e to the minus j omega t naught x of j omega. So now we can combine these two by looking at our t naught values. So for the first section of this, our t naught is just going to be equal to 1. And for the second section, our t naught is going to be equal to -1. And then we know that our x of j omega for these is just going to be equal to 1. So we can combine these two properties to get x of j omega is equal to e to the minus j omega t naught x of j omega, which is going to give us x of j omega is equal to e to the minus j omega times 1 plus e to the j omega times 1. And then we can simplify this down a bit farther using Euler's formula. If we multiply in 2 over 2, we get 2 times e to the minus j omega plus e to the j omega over 2, which we can simplify down to 2 cosine of j omega. Any questions on that?
I have a quick question. If
Yeah.
you were multiplying the delta functions by like 2 or like let's say 4, would your x become that number?
So
X j omega representing?
So the x of j omega is representing the Fourier transform of that. So in this case, we identified the Fourier transform of the delta function to be 1, and then we identified that they're time shifted by t naught amount, and then we applied that property to the Fourier transform of the delta function, which is 1. If you had like a 4 in front, for example, you would end up with 4 times that, but you wouldn't be changing your x of j omega value. It would still just be 1, but you would also include the linearity property. So you would carry that 4 through. So you would get 4 times your x of j omega, which is 1. So you would just get 4. Does that make sense and help explain?
Yes, thank you so much.
Okay, absolutely. All right, so there is a second problem on the PowerPoint and everything. We're gonna skip this, and I'm gonna post the work for it. Feel free to try it on your own. It's pretty similar to the first problem, so I have high hopes for y'all being able to do it. Let's jump into 6B, and this will be our last question. So we made a mistake on the PowerPoint for this question. If you're looking at it, it says find x of j omega or h of j omega. We really want to find h of t. So I just corrected that on here, but just make sure you're aware of that. So the first step is we want to take the Fourier transform. And if we consult back to our properties table, there's 2 properties we can use here. Differentiation and linearity. So linearity, you're just going to carry through any coefficients that are amplitude scaling. And then for differentiation, each derivative becomes a j omega times x of j omega. So for our first term here, we don't have any scaling coefficient. So we're going to get j omega squared, because it's the second derivative, times y of j omega. And then for our second term, we have the linearity with the amplitude scaling. And then we have j omega times y of j omega. And then for our final term on the left side, we have linearity again. And then there's no differentiation, so we just get y of j omega. We're going to do the same thing for the other side. We're going to get j omega squared, x of j omega, plus 3 j omega, x of j omega, plus 2x of j omega. Now, we want to find the transfer function. And the definition of the transfer function is y of j omega over x of j omega. So we want to rearrange this equation to be in the form y of j omega over x of j omega is equal to something. So the way we're going to do that, every term on the left is multiplied by a j omega, or a y of j omega, and every term on the right is multiplied by an x of j omega. So we can go ahead and factor those out. So we're going to get y of j omega times j omega squared plus 6 j omega plus 8 is equal to x of j omega times j omega squared plus 3 j omega plus 2. Sorry, I missed my parentheses here. All right, and now we can divide both sides by x of j omega and divide both sides by j omega squared plus 6 j omega plus 8 to get the form y of j omega over x of j omega, which is equal to our transfer function, h of j omega, and that's going to be equal to j omega squared plus 3 j omega plus 2 divided by j omega squared plus 6 j omega plus 8. Now, we're going to do partial fraction decomposition. So we need to factor our denominator. So we're going to leave our numerator the same. Oh, sorry. And then we're going to find the roots of our denominator. So in this particular case, our roots are going to be j omega plus 4, j omega plus 2. So now for our partial fraction decomposition, we can go ahead, we can take this term, j omega squared plus 3j omega plus 2 divided by j omega plus 4 times j omega plus 2. And we're going to set that equal to a over j omega plus 4 plus b over j omega plus 2. We want to solve for our a and b coefficients. So we're going to go ahead and multiply the j omega plus 4 and the j omega plus 2 over. And we're going to get j omega squared plus 3j omega plus 2 is equal to a times j omega plus 2 plus b times j omega plus 4. Now we can distribute out our a and our b. So we're going to get j omega squared plus 3j omega plus 2 is equal to a j omega plus 2a plus b j omega plus 4. And now we can solve this using coefficient, what is it called? Coefficient correlation, I think is what it's called. So we're going to set up two equations. We're going to solve them. So our first equation is we need to look at our j omega terms on each side. And that's going to give us the equation a plus b is equal to 3. Then we need to look at each term that doesn't have a j omega. And that's going to give us 2a plus 4. Oh, sorry, this should have a b on it. 4b is equal to 2. And now we can use this system of equations to solve for our a and our b. So we can just subtract over b on this side and get a is equal to 3 minus b. And substitute that in over here. And we're going to get 3 times 2 is equal to 6 minus 2 times minus b. So that plus 4b is equal to 2. Simplify this down to 2b plus 6 is equal to 2. Subtract over the 6 gives us 2b is equal to negative 4, which means b is equal to negative 2. Now we can substitute that back into our first equation and get a minus 2 is equal to 3, which gives us a is equal to 5. So now we solved for our a and our b, and we can plug them back in to get our h of j omega is equal to 5 over j omega plus 4 plus negative 2 over j omega plus 2. Yeah, perfect. So now we have our transfer function in the frequency domain. Now we need to inverse Fourier transform it back into the time domain. So we're going to use our tables for this. And I didn't put the tables on this, but you can find them on the slides on slide 10. So we have, let's rewrite this out as 5 times 1 over 4 plus j omega plus, sorry, let's do minus 2 times 1 over 2 plus j omega. And now we can see for 1 over 4 plus j omega and 1 over 2 plus j omega, we're going to use, that's going to turn into e to the minus at u of t in the time domain. And then we just carry through our coefficients. So we're going to get h of t is equal to 5 times e to the minus 4 t u of t minus 2 e to the minus 2t u of t. And that's going to be our answer for our impulse response. Any questions on that? All right. If there's no questions on that, I think we're done. If you have anything else, feel free to stick around and ask us quick. Other than that, I think we're done and good to go.
Hey, could you show could you go up to 6A for a
To 6A?
second?
Yeah.
Yeah, thank you.
Did you have a question on this?
I'm just one. Could you zoom out a little bit so I could possibly see the whole thing? Okay, thank you. Okay. I think I'm good.
Okay.
With this.
Awesome. Does anybody else have anything?
Sorry. How did you divide? Wait, never mind. You divided by 2 because you wanted the euros, I'm assuming.
Yeah, I just did that. I multiplied by 2 over 2 just to get into Euler's form. So that's why you get the 2 cosine.
Okay, thank you.
Absolutely. Any other questions? All right.
Can you please go back to the problem we just did?
Yeah.
Okay.
Let me know if you need to see a specific part of it or anything.
Yeah, just the ending part, the last
Okay.
part.
Sorry.
Thank you. Okay, I'm good. Thank you.
Okay. Awesome.